Hello everyone, I am Ramya here. So our team is here to present on the topic cubic spline interpolation and differentiation. So cubic spline interpolation. Interpolation is the process of estimating values between known data points. Suppose that we have a set of data points and we want to create a smooth curve that passes through all these data points. So this cubic spline interpolation is a technique which is used in numerical methods in order to achieve this. It works by fitting a group of cubic polynomials that are polynomial of degree 3 piecewisely through all these data points. And after that, we have constructed the cubic spline. We will get a curve that is called the spline. And after that, we can find the derivative. So it will help us to understand how steep or shallow our curve is at a given point, at a given data point. And next is these cubic polynomials are carefully chosen in such a way to ensure that the resulting curve called spline has the following properties. They are interpolation, continuity, and smoothness, which is an optional. And the first property is interpolation. The spline, this means that the spline should pass through all the given data points. And next property is continuity. The spline should be continuous across all the intervals between the data points. This means that there should not be any jumps or gaps between the curves. And the last property is smoothness, which is an optional one. In some cases, we may also need the curve to have continuous first derivative, which means that the slope should be continuous across the intervals between the data points. So this ensures the curve to be even smoother. Next is the end-day processes or steps of cubic spline interpolation and differentiation is these given data points, interval division, constructing of cubic polynomials, imposing conditions, continuity conditions, solving equations, evaluating the splines, and derivative of cubic spline. The first step is given data points. Suppose that we are given n data points and let x1, y1, etc. up to xn, yn be those data points. And next is interval division. We will divide the entire range of data into intervals, and each interval xi plus 1 will have its own cubic polynomials. And next is constructing of cubic polynomials. Within each of these intervals xi plus 1, we will construct a cubic polynomial which is of this form. Si of x is equal to ai into x minus xi the whole cube plus bi into x minus xi the whole square plus ci into x minus xi plus bi. Next is imposing conditions. We will impose interpolating conditions to make sure that the spline passes through all the given data points. And interpolating conditions is given by si of xi is equal to ya and si of xi plus 1 is equal to ya plus 1. Next, we will also impose continuity conditions to ensure smoothness between adjacent intervals. And the continuity of function values is defined as si of xi plus 1 is equal to si plus 1 of xi plus 1. Continuity of first derivatives is given by si dash of xi plus 1 is equal to si plus 1 dash of xi plus 1. And continuity of second derivatives is given by si double dash of xi plus 1 is equal to si plus 1 of double dash of xi plus 1. Next is solving equations. We will solve the resulting system of equations in order to find the coefficients ai. In order to find the coefficients ai, bi, ci, and di of the cubic spline function that discussed earlier. And next is evaluating the spline. Once the coefficients are determined, the spline function at any point can be determined by determining the interval it belongs to and calculating the following spline equation at that corresponding point. Next is derivative of cubic spline. Once we have a spline function s of x, we can differentiate it to find the derivative s dash of x. Next, my teammate will continue with a problem. I have to show a programming problem. The ring is added into. Okay. Okay. Good morning, all.
Ramya taught all the introduction part of this cubic spline interpolation, and now I am going to implement it through analytically and using Python programming. So this is the question, which obtain the cubic spline of the following data and find y of 2.5 and y dash of 3. And this is the points x and y. X from 0, 1, 2, and 3, and y varies from 2, -6, -8, and 2. And so I have to do the problem. Okay, this is the question for doing this analytically, and obtain the cubic spline of the following data and find y of 2.5 and find the derivative of 3. Okay, this is our points x, y. X is 0, 2, 0, 2, y -6, and x is 2 and y is -8. Okay. We can't move the slides. Can you please? Same. Okay, for doing this analytically, we need two equations or two formulas, finding the boundary values and find the cubic spline polynomial. Ramya already told about what is the format of that equation that we get after solving this. And it is of the form Si of x is equal to Sai into x minus xi the whole cube, like that. Okay, now we are going to use these two formulas for finding the boundary values and finding the cubic spline polynomial. And here m is the boundary values, and we are finding s of x by using this equation, where h is the step size and mi are the boundary values. Okay, here our step size is 1 because our points are like x, y, 0, 1, 2, 3, and y points are 2, -6, -8, and 2. So from that points we can we get h is equal to 1. So I write it here. H is equal to 1, and we need n value. N is, we have 4 points. N starts from 0 to I minus 1, so it varies from 0 to 3. So n value is 3. N is equal to 3. And now I am going to find the boundary values for this is to this thing is for every questions that solving cubic spline interpolation, m0 and mn will be 0. for every problem of cubic spline, M0, boundary values M0 and M1 will be 0. So we have to find M1 and M2. Okay, M1 and M2 we have to find. So for finding M1 and M2, we have to use Mi minus 1 plus 4 Mi plus 1 plus Mi plus 1 is equal to 6 by x square into yi minus 1 minus 2yi plus yi plus 1. This is the equation that we are going to use. So we have to substitute the values of 0 here. Values of m0 and mn 0 to this equation, and we will get answer as so. Yes. So we got the values m0, mn is equal to 0, and we are going to find m1 and m2. So mi minus 1 plus 4mi plus mi plus 1 is equal to 6yi minus 1 minus 2yi plus yi plus 1. So here it's there is no h because its values is 1. So I just ignore it. And mi minus 1 is I is equal to 1 because and so I is equal to I minus 1, 1 minus 1 is equal to 0. That m0 plus the equation will become this is the equation m0 plus 4m1 I is equal to 1. So for m1 plus mi plus 1 is 1 plus 1, that m2 is equal to 6 yi minus 1 y0 minus 2y1 plus y2. So this is the equation 1. And for I is equal to 2, the equation will become m1 plus 4m2 plus 4m3 is equal to 6y1 minus 2y2 plus y3. Any doubt? Anyone don't understand? Any doubt? Clear? Okay. Okay, this is the equation 2. So we are solving these two equations, 1 and 2, and we will get 4m1 plus m2 is equal to 36 and m1 plus 4m2 is equal to 72. So we are solving these two equations. Lots of calculations. So I just write the values of m1 and m2. Any doubt? No? Okay. So we get the values of m1 and m2 as 4.8 and 16.8. So we put these two values in this equation. S of x is equal to 1 by 6. Here also h is equal to 1. So I just write this equation. S of x is equal to 1 by 6 xi plus 1 minus x the whole cube mi plus 1 by 6 x minus xi the whole cube mi plus 1 plus xi plus 1 minus x yi minus 1 by 6 mi plus x minus xi yi plus 1 minus 1 by 6 mi plus. This is a little hard equation, so we have to by heart it, something hard to do. So I'm going to put these values of m1 and m2 in this equation, and first of all, the x and y points are 0, 1, 2, 3, and y points are 2, minus 6, minus 8, and 2. From points, there is 3 interval that in between 0 and 1, 1 and 2, and 2 and 3. So 3 intervals and we get 3 cubic spline polynomials. Okay. We have 3 intervals and we have to find a cubic spline polynomial for each of these intervals. So we have to solve this S of x equation 3 times to get 3 cubic spline polynomials. So this is the interval 1, interval 2, and this is the interval 3. So for finding first cubic spline polynomial on the interval 0, 1, we are, I just put the values here. S of x is equal to 1 by 6, 1 minus x cube into 0. 0 means that mi m0, that mi minus 1 is equal to 0. So that value is 0. Plus 1 by 6 into x minus 0, the whole cube. Here also it is mi minus 1 into 4. So I just put the values on this equation, that formula that I showed earlier. Okay. As of for finding the cubic spline polynomial for the first interval 0, 1, our for I just put the values. S of x is equal to 1 by 6 into 1 minus x the whole cube. The 6 is already in that equation. So 1 by 6 into 1 minus x the whole cube into 0 plus 1 by 6 into x minus 0 the whole cube into 4.8 plus 4 is the value of m1. 4.8 plus 1 minus x into x minus 0 plus x into minus 6 minus 1 by 6 into 4 minus 8. Minus 6 is the value of fi plus 1. Okay. Fi plus 1, that is y2. Our values are x, y, 0, 1, 2, 3, 2, 2, minus 6, minus 8, and 2. So we are putting the values here and we find the first cubic spline polynomial. For finding the cubic spline polynomial is a little bit tricky. So I just write the polynomial here. 0.8 the whole cube minus 8.8 x plus 2. This is the first cubic spline polynomial of the interval 0 less than or equal to x less than or equal to 1. So for finding any derivative or values of y in this interval 0 and 1, we use this polynomial for finding that. Okay. Any doubt? So our question was find y of 2.5 and y dash of 3. So these two points are not in this interval. So we have to find that polynomial of that polynomial in that interval 2, 3. So the polynomial that we are going to find these two things by using this polynomial. Okay. We are just putting the values in that formula and finding the polynomial. There is no much confusion. The values are already there. Okay, finding the polynomial for the interval 1, 2 is on the interval 1, 2 is s of x is equal to 1 by 6, 2 minus x the whole cube into 4.8. This is m1. plus 1 by the 1 by 6 is already in that formula. S minus 1 the whole cube into 16.8. 16.8 is 1 M2 plus 2 minus 6 into minus 6 minus 1 by 6 into 4.8 plus x minus 1 minus 8 minus 1 into 16.8. So we get the polynomial as 2x cube minus 5.84 x square minus 1.68 x plus 0.8. This is the second cubic spline polynomial in the interval 1, 2. Okay. Okay. This is the same thing done in this interval also. For finding the polynomial in this interval 2, 3, and we get the values, get the polynomial as this, and we are using this polynomial for finding y of 2.5 and y dash of 3. We are finding this is s of x, and we get we just put the value 2.5 in this place, x place. Okay, by using the third cubic spline polynomial on the interval 2, 3, we put the value 2.5 and in the cubic spline polynomial, and we get the value of y of 2.5 as 13.4, and then find the derivative of the derivative of that polynomial, and we get it as minus f dash of x is equal to, or s dash of x is equal to minus 2.4 x square plus 5.28 x plus 9.6. This is the first derivative of that cubic spline polynomial on that interval 2 and 3. And we just substitute the value of x with the since we have to find y dash of 3. Just put the value of 3 in that equation, and we get it as we get the value of y dash of 3 will is as we get the value as y dash of 3 is equal to 9.4, and this is the value, and we find the value of y of 2.5 and y dash of 3 here through doing analytically, and now we are going to implement it through programming. Okay, this is the Python implementation of cubic spline interpolation, and there is no much. What will you do? I want to really finish this presentation. Okay. I will do it. Okay, this is the Python implementation of cubic spline interpolation. We don't have to do some hectic work here. Just first import number as np and import matplotlib dot pyplot as plt, and from scipy interpolate we have to import cubic spline, and we just give the data points as array. X is equal to np dot array and y is equal to np dot array of 2 minus 6 minus 8 and 2, and we just call the cubic spline x comma y in the object cs, and for finding x spline is equal to nb dot linspace min x, max x. That min x is 0 and max s is 3, and we divide this interval as into 100 points. So the graph will look like this. Okay, this is the smooth curve that we get by this is the green points are the data points, and this blue line is the cubic spline interpolation curve that we get here. This is the way to find the cubic spline interpolation. And for finding the derivative, we just need to derive it, that CS dot derivative of this nu is equal to 1 means the first derivative, and nu is equal to 2 means the second derivative, and of x plane. And we just find the value of y of 2.5 and y of 3, first derivative of 3 here, and just I plotted here using this and I got it as this simplest we can do in programming. We don't have to do any formula or some hectic things. So this is the thing, implementing through a program. That's all. Application is done.
I am Abhyami AS. Now I am going to tell about the applications, advantages, disadvantages, and challenges. First, we have weather prediction. The I will give some rough sketch on the weather prediction. Okay, the x-axis denote the some x. I will give an example of weather prediction. The x-axis denote the weather stations, and the y-axis denote the temperature. And we will get a graph like a curve, but we can using. But there are a lot of gaps between these x-axis, and there will be noise. Through cubic spline interpolation, we can interpolate this graph, and we will get a approximated temperature. This is like a rough sketch. Don't take it serious. And through cubic spline interpolation, we will get an approximate temperature. And this mainly while taking a actual graph, there will be noises. These noises are mainly due to the temperature variations along the weather stations. So using cubic spline interpolation, we can approximate it. And next we have speech recognition. Speech recognition means speech recognition translate a spoken words into text word. So using cubic spline interpolation, we can interpolate like this graph. We know human voices can vary constantly. Human voices have pitch varies constantly, and its pitch and volume changes constantly. So there will be many fluctuations in our voices. So we can see that there will be many fluctuations. So through using cubic spline interpolation, we can we can this cubic spline interpolation used to fill the gaps between fluctuations means these cubic spline interpolations understand the noises and tiny fluctuations of this graph. So we can use this cubic spline interpolations. We can using the cubic spline to interpolate like this, and through this the speech recognition engineers can easily identify the each fluctuations and any missed informations from this graphs. And next we have next we have traffic engineering. Traffic engineering means engineers can through cubic spline interpolation they can easily understand the traffic patterns, if any we can in future is there any traffic happens through this cubic spline interpolation they can identify and
അത് ക്ലോസ് ചെയ്യും. ഇനി അത് ക്ലിക്ക് ചെയ്യും. ഇവിടെ ക്ലിക്ക് ചെയ്യും. ഇനിയാണ്.
Next, medical imaging. Medical imaging means we all know about the CT scan and the MRI scan. These are used to identify our internal anatomy. This works on these internal anatomy is each is in a slices. Each slices means pictures. So there will be some gaps. There will be some missing information while visualizing these scans. Through cubic spline interpolation, the doctors they can easily interpret the medical condition and they can easily diagnose the patient. So in medical imaging also cubic spline interpolation using. Next, I am taking about the advantage of the cubic spline interpolation. First, we have smooth and accurate curve. We already seen that cubic spline interpolation graph will give a we already seen in the graphs like this, it give a smooth curve. This is the actual curve. Through cubic spline interpolation, we will get some smooth and continuous curves. This is the I think major advantage of the cubic spline is the smooth and continuous curve, and the smoothness we can see that. Moreover, cubic spline interpolation dealing with the unevenly spaced data, we can but in some interpolation techniques which does not lead with the unevenly spaced data, but through cubic spline interpolation we can do. Next, reduce errors and noise. We have seen that in the actual graph there might be more noises and errors, but through cubic spline interpolation we will get it correct the all noises and errors, and we will get a smooth and continuous curve. and smooth and continuous curve. Next, efficient computation. We can like in this cubic spline interpolation, there will be using Thomas tri-diagonal algorithm, which is and in cubic spline interpolation, we can prefix the cubic spline coefficients also. So there will be computationally efficient, but this is also a challenge, and we will see it later. Challenges. Overfitting. Overfitting means this cubic spline can fit this also. This is the last. Overfitting endpoint behavior computation called extrapolation issue. Sorry. Sorry. I need to explain. Overfitting means we know that the model can fit the data to the model can fit the data too well, but when a new data arrives, the model cannot fit the data. So that is overfitting. There will be a and we will get an unrealistic graph. So which is a challenge. And next, endpoint behavior. Cubic spline interpolation behaves in a, which interpolate the data in a within a region. So beyond the region, within a region. So beyond the region, which is unrealistic, and computational cost, and which we have seen that it is as an advantage. Computational cost. But for taking larger data sets, cubic spline interpolation cannot interpolate because we cannot, which is computationally, we need more computational requirements. So next we have exploration issues. Exploration issues means we have seen that interpolation is within the ranges. So beyond the ranges, which is also unrealistic. Conclusion: cubic spline interpolation is a good interpolation, which also have limitations and advantages. Thank you.
Not outside, inside.
Yeah, here they can get you. Better I can write here.
Wait.
Special purpose. I want to record it. Okay. So this is what I taught you yesterday. This is from Andrew Ng, founder of machine learning. So you watch his lectures also, but it is very different from what I taught you. This is more.
Okay.
Just type on YouTube Andrew Ng gradient discipline.
Since the times, human was always exploring and exploring the nature, exploring himself, exploring everywhere for what? For to get better understanding over the nature and the predictions for future predictions. Human have since the since the times of Mayans, ancient Greeks, ancient India, there were a lot of astrological sciences just to predict the future. Predicting the future is because of the curiosity that human wants to know what happens next. But philosophically, some question arises like, what if we came to know, like, what if we know everything, what happens next in our future? Just we can take example of character from Mahabharata, Sahadeva, one of the Pancha Pandavas. He was a Trikala Jnani, like he knows everything what happens next in the future. Life seems like very boring, no? He knows everything what happens in the future. Still, human is behind that. He wants to predict what happens next. Okay. This story comes from there. Like, this story started in the attempts for predicting the weather. Edward N. Lawrence, a meteorologist, American meteorologist, exact pronunciation, meteorologist from Massachusetts Institute of Technology. He was working on 12 different parameters of weather to predict, so to model the weather. What we came to know that is a tiny change in the initial value. We can only predict the things if we know, if we have some data from the past. So initial changes, tiny changes in initial conditions can have a huge impact, have a huge difference in the future. Just like there's a saying, if we type butterfly effect, we get some 50, 60 movies and thousands of videos in across YouTube. So butterfly effect means if a butterfly flaps its wings, and it can cause some tornado, some thousands of kilometers elsewhere. Like, yeah, the theory comes like that. The tiny things in the present can have a large impacts in future. Then another philosophical question arises: if this theory it really exists, like how many kills I have done by my sneezing? Still till now, like, yeah, just some. Yeah. Okay, let's get into this. Next slide. Yeah. Next slide. These are some spirographs in childhood we have played. Okay, in childhood most of us played like these loops. They go like these are the loops exactly. Like once you have started the pen, it will end up joining to the same point that you have started after some periods. So these are loops actually, but we are going to look into something that never reaches, infinitely never reaches to its initial point. Lawrence developed some mathematical model while predicting the weather, that's known as Lorentz attractor. These attractors are a set of points in a space toward which neighboring points are symptomatically approach within a basin of attraction. What is that? Okay, if you can better understand, if we visualize it, we are going to visualize it now. Okay, an attractor can be a point, curve, manifold, or a complicated set of fractals known as a strange attractor. So here's another term, fractals. What is a fractal? Fractal is some geometrical figure that go on repeating. Means the large, the large geometrical position goes on repeating itself within itself like that. You can take the example of golden rectangle, like, okay.
Not that. What do you mean? Here. Not this end. What do you want?
Okay. Okay. This is okay. This whole rectangle, it goes on repeating in this, like if you plot a square here and this rectangle resembles this rectangle resembles this. This is the concept of golden rectangle and sorry, golden rectangle, and the ratio between the sides, that's the golden ratio that most of us, like most of you know. So next slide.
Next slide.
Um, okay, then what's the strange attractor? An attractor that exhibits sensitive dependence on initial conditions. They usually have fractal structures. Yeah, we will better understand this when we have visualizations. There are some examples for the strange attractors here. Okay.
Next.
These are some examples. We are just looking into the Lorentz attractor now. He's the that meteorologist, Edward Lorentz, who just gave 3 equations to show how initial conditions are leading to very great differences, very great unpredictable conditions in future. Yeah, the Lorentzian water wheel actually can okay. Yeah, okay, it's fine. Next, it's the Lorentzian water wheel. Like these all the
You want to
cups. These all the cups have some
number and
a hole in their bottom, and water is being filled from upwards. Yeah, if we like, you can YouTube it and watch that Lorentzian water wheel. That law of, these are 3 equations, Lorentz equations, that we can better understand. These are what variables and the constants explain when it's applied. Those equations are applied to the fluid dynamics. Okay, next. Yep. Okay. Here, one important thing we can notice here is okay, for in all the 3 graphs, for first initial initial period, we can predict the graph, but after that the system goes very chaotic. We can't very unpredictable. We can't predict the stuff exactly. That's why whether we can predict the weather for only 5 to 9 days with some accuracy. After that, we can't predict weather certainly. The predictions goes with high uncertainties.
next.
Yep. Then what will be the implications for implications of this concept for the numerical computation? Okay, as we are dealing with a lot of data, the numerical computations, like they means different algorithms, different pipelines, they can cause some fault, like some differences in our calculations or predictions, and they can have a huge practical impact on the real life world. So that's why we should be very clear in the theories of the numerical computation as data analysis.
Slide.
Yeah, the next part is going to
Into a problem, we have to determine the stability of the fixed points of the Lorentz system for sigma equal to 10, rho is equal to 8, and beta equal to 8 by 3. So we know the Lorentz equations are dx by dt equal to sigma into y minus x, dy by dt equal to x into rho minus z into minus y, and dz by dt equal to xy minus beta. So to find the fixed points, we have to solve the points. We have to set the derivatives to 0. So we have to equate the derivatives to 0. The first equation would be sigma into y minus x equal to 0. From then we get y minus x equal to 0 and y equal to x. From the equation, x into rho minus z minus y is equal to 0. We have to substitute y equal to x into this equation. Then we get x into rho minus z minus x equal to 0. From this, we get x equal to 0 or rho minus z minus 1 is equal to 0. It will be z equal to rho minus 1. So we get two possibilities, x equal to 0 and z equal to rho minus 1. So we have to consider the first case, x equal to 0. We know y equal to x, then y would be also equal to 0. Then substituting x equal to 0 and y equal to 0 into the third equation. The third equation would be xy minus beta z is equal to 0. Then substituting x and y equal to 0, we get z is equal to 0. So we get the first fixed point as 0, 0, 0. This is our first fixed point. Now let's next consider the second case where z is equal to rho minus 1. And substituting it into the third equation. This is the third equation. We get by solving this, we get x equal to plus or minus root of beta into rho minus 1. Since y is equal to x, we also get y as plus or minus root of beta into rho minus 1. Therefore, the second fixed point will be and the third fixed point will be negative beta rho minus 1, comma negative beta rho minus 1, and rho minus 1. Now we have to substitute the values of beta and rho. In the question, they have provided the value of sigma is equal to 10 and beta is equal to 8 by 3 and rho is equal to 20. And the root beta rho minus 1 will be root of 8 by 3 into 20 minus 1. We get
root of 72, which will be equal to 6 root 2. So the fixed points are 0, 0, 0, and 6 root 2, 6 root 2, 27, and minus 6 root 2, 27. Now we have to determine the stability of this fixed points. So we have to find the Jacobian matrix for that. Jacobian matrix would be minus sigma, sigma 0, rho minus z, minus 1, minus x, y, x, minus beta. We get this Jacobian matrix by from the Lorentz equations, and to find the then we have to find the eigenvalue to know the stability of this equation. Then we can find the eigenvalue by determinant of j minus lambda I equal to 0. Then substitute the value of sigma, beta, rho, x, and y. From here we get minus 8 by 3 minus lambda is equal to 0. We get lambda 1 is equal to minus 8 by 3. That is the first eigenvalue. Then we have to find the determinant of then we get lambda plus 10 into lambda plus 1 minus 2x. It would be lambda square plus 11 lambda plus 10 minus 280 is equal to 0. By solving this, we get lambda 2 is equal to 11.827 and lambda 3 is equal to minus 22.827. So here the lambda 2 is positive and lambda 1, lambda 3 are negative. So the fixed point 0, 0, 0 would be unstable, which means the origin is unstable and all points start close to origin will eventually leave this region. Now we have to find the Jacobian matrix and eigenvalue at the point 6 root 2, 6 root 2, 27 as same as this. We also, by solving that, we get a complex conjugate eigenvalue with the positive real part and one negative real eigenvalue, indicating that that point is also unstable and lead to chaotic behavior. The Lorentz, so it means the Lorentz attractor is not a stable equilibrium. In fact, most all trajectories will approach the Lorentz attractor but never reach the equilibrium.
No, sir, with the code.
Good morning, everybody. I'm Alvin, and I'm here to talk about the code which depicts the or plots the Lorentz attractor. And we can see that we have three libraries which have been used to plot the graph. As we have been using Matplotlib for a few times. We know what the library does. It plots the graph, and to make the graph 3D, we have imported another library That is also a subset of Matplotlib library, which can, from the library, we have imported a specific part, which is the Access 3D. And we have also imported NumPy for the use. And we have also defined the parameters that we are going to use. For the sigma value, we are going to assign 10, and for the rho 28, and for beta 8/3, which we have seen from the questions that were done before. And for the time simulation that have been given, we have been given 100, which is a unit of time for which the simulation will work and give us the plot output. And the number of steps can be taken as the integer output of the values t divided by dt, which will be 1,000, 10,000. And we have initialized x, y, and z, which is a NumPy array of zeros, and the number of condition or number of values that it has is the number of steps which is mentioned above. And the initial values of each of these arrays are given as 1, which is the initial condition. Since we cannot start with 0, 0, 0 as it goes unpredictably so little, we have given the values as 1. And for these steps, we have given it through a loop where we use the equations such as dx by dt equal to sigma times y minus x, which is written in such a form that dt is multiplied with the values sigma, and each values of the array are taken and it is iterated, and the values will be appended to the list after the calculation. That's the last 3 steps which we have been looking at. And for the plot, we have assigned the figure variable as the plt.figure. And for the axis, we have added a subplot which will mean that the values 111 means that the cross section, the values of plot with 1 by 1 cross 1 values, and 1 will suggest that it is a subplot, the last one. And the projection is a 3D projection. And for the plots, we will use the x, y, and z values which we have been iterated and storing in an array. And the line width with which we have plotted will be of thickness 0.5. And we have assigned the labels to each of the coordinates and the title. And for the simulation, we will look how the plot will work when we run with these codes. So this is the plot that we will get when we give the initial values of 111 and the sigma values, sigma rho and beta values which were given. We can see that the behavior is quite chaotic and we are not able to predict. We won't, to a certain, we won't be able to predict what the or how the particles will move or molecules will behave when given certain conditions. If we change with the parameters that were given above, we can see that we'll be able to understand that the graph which it produces are of different kinds. This is the beauty and the terror that we face with when we play with Lorentz system. With this, we conclude our presentation. Thank you.